Welcome to today's deep dive. We are exploring a highly specific, really intense tactical maneuver used by firefighters. It's called positive pressure ventilation, or PPV.
Yeah, and the source material we're working from today is actually a strict, meticulously detailed practical exam guide.
Right. To pass this state exam, candidate firefighters are basically given a relentless stopwatch. They have exactly 4 minutes and 40 seconds to complete the entire operation.
Which is just an incredibly short amount of time for what they're doing.
It really is. So the mission of this deep dive is to unpack the surprisingly precise, high-stakes physics and, the complex choreography that firefighters use to clear a burning building of deadly smoke and heat.
It functions essentially as a manual for performing applied fluid dynamics under extreme life-or-death conditions.
Because usually when we think about firefighting, we picture water, right? Like a massive directed stream from a heavy fire hose just knocking down flames.
Exactly, yeah. Water is physical, it's visible.
It's highly tangible. You point a nozzle and you can see the immediate visceral effect on the environment.
Right, you observe the fire, you watch the water smother it, and you see the flames extinguish. The cause and effect relationship is just very straightforward and observable.
But with this, I want you to imagine for a second trying to solve a complex fluid dynamics puzzle where your primary tool isn't water, but an entirely invisible force.
An invisible force, exactly.
And you are having to solve this invisible puzzle while wearing like 60 pounds of heavy thermal gear in a completely dark, incredibly hot environment.
Yeah, it's intense.
By the time we finish unpacking this exam guide, I promise it will completely change how you look at the simple act of opening a window or turning on a fan in your own home.
Absolutely. Because, before anyone even thinks about turning on a massive industrial fan, the exam guide requires the candidate to verbalize a very rigorous set of preparations.
Right, the setup phase.
Yeah. The transition from a chaotic emergency scene into a deeply calculated strategic operation begins with situational awareness. Candidates must announce they are in full personal protective equipment.
Makes sense?
And they must declare they are actively monitoring for an IDLH environment.
Right, and for those unfamiliar with the acronym, IDLH stands for immediately dangerous to life and health.
Exactly.
If that environment is present, the guide dictates that candidates must immediately go on air, meaning they start breathing entirely from their SCBA oxygen tanks.
And let us pause and just consider the sensory reality of an IDLH environment.
Yeah, paint that picture for us.
Because this is not simply a smoky room. We are talking about zero visibility, where the particulate matter is so dense it completely absorbs the light from heavy-duty flashlights.
Oh, wow. It absorbs the light.
Yes, and the air itself is superheated, filled with toxic combustible gases like carbon monoxide and hydrogen cyanide.
So it's basically a sensory deprivation environment combined with an oven.
That is exactly what it is, and that is the baseline reality for the interior crew.
Right, the people actually inside the burning building.
Yeah. The exterior crew, the candidate taking this exam, has to operate knowing their colleagues are crawling through that exact environment. So the prep work reflects that danger.
Which is why they have to check off all those boxes first.
Yeah, the candidate must confirm they have shut down the utilities to the building to prevent gas explosions or electrocution.
Okay, that makes sense.
And critically, they must establish a secondary means of egress.
Like a backup exit.
Exactly, a backup exit, usually a ladder to a second-story window or cleared back door, just in case the ventilation plan fails and the interior crew needs to bail out instantly.
So coordination is the bedrock of this entire maneuver.
Oh, absolutely. Command must explicitly authorize the use of positive pressure ventilation.
You can't just go rogue and turn on a fan.
No, definitely not. The exterior crew setting up the fan must be in absolute synchronization with the interior crew fighting the fire. Pushing massive volumes of air into a burning structure without that coordination is just a recipe for disaster.
Which brings us to the core physics principle outlined in the guide, something I am calling the golden rule of pressure.
I like that name.
The source material states that the exhaust outlet, which is typically a window somewhere in the back of the structure, has to be opened first.
Right.
And the absolute critical factor here is that the exhaust outlet must be smaller than the inlet, which is usually the front door.
Yeah, the guide actually provides a very stark mathematical example to illustrate this.
Okay, let's hear it.
So if the front door inlet is approximately 20 square feet, The selected window, acting as the exhaust outlet, needs to be roughly 10 square feet.
Half the size.
Roughly, yeah. Furthermore, there can only be one designated outlet used for the entire structure.
Just one.
Just one. The firefighter is required to physically remove any curtains, drapes, blinds, or heavy furniture that might be blocking that single window.
You know, I like to visualize this single, smaller outlet rule by picturing a Red & Garden hose.
Okay, yeah.
If you have a hose and you poke like 5 different holes along the rubber, the water pressure becomes completely weak. It leaks everywhere, uncontrollably, and you get no distance on the spray.
Right, you lose all the force.
Exactly. But if you take your thumb and cover the main nozzle, creating one single perfectly sized, unobstructed hole, you create a powerful, highly directed, high-pressure jet.
That analogy captures the mechanics perfectly. You are essentially turning the architectural footprint of the entire building into a pressurized vessel.
Wow.
By keeping the exhaust outlet strictly smaller than the inlet, the fan pushes more air into the building than can immediately escape.
Right, so it builds up.
Yes. This creates a higher air pressure inside the structure compared to the outside atmosphere.
I have to question the sequence of events the guide lays out, though.
Oh, how so?
Well, the rules dictate that you must open the exhaust window before turning on the fan.
Right.
If there is a crew inside a burning building, crawling on the floor, choking on zero visibility smoke, my first instinct would be to blast the fresh air in immediately to give them some relief.
It's a natural instinct, sure.
Right. Taking the extra time to run all the way around to the back of the house to properly stage a window seems like a waste of precious seconds when you only have 4 minutes and 40 seconds.
I get that, but blasting forced air into a structure before that specific exhaust route is fully staged is incredibly dangerous.
Really? Why?
Because if you introduce a massive volume of forced air without a designated mathematically proportional exit, or if, say, multiple windows are randomly open throughout the house, the pressure simply drops.
So you'll get that jet effect.
Exactly. You fail to create that powerful directed jet of clearance. The air just scatters indiscriminately.
Oh, I see.
And worse, the smoke and toxic gases are pushed violently into uninvolved areas of the house. You lose all control over the environment.
That sounds like a nightmare.
It is. Instead of clearing the main hallway, you could be forcing superheated, deadly gases into a closed bedroom where a civilian is sheltering.
Oh, wow.
Or you could completely blind the interior crew by surrounding them with dense smoke. The math of the pressure difference dictates survival.
That makes a lot of sense.
If the exhaust isn't smaller, or if there are too many exhaust points, the pressure equalizes prematurely, and the entire ventilation tactic just collapses.
Okay, so the exhaust window is properly staged. The proverbial thumb is securely on the hose. The building is mathematically prepped to act as our pressure vessel.
Right.
Now we transition to deploying the fan itself. And the source material treats placing this fan as an exact spatial science.
It really does.
You don't just drag a heavy blower up to the front porch, point it at the door, and turn it on.
No, the spatial parameters are extremely rigid. The fan must be positioned approximately 6 feet away from the inlet door. Right. And whenever operationally possible, the guide notes that this entire setup should happen on the windward side of the building.
Letting natural wind assist the mechanical fan's performance, right?
Exactly.
Using the ambient weather to help build up that interior pressure so the machine doesn't have to do all the work alone.
Yes. And the choreography of actually starting the equipment is particularly fascinating.
This part blew my mind.
When the firefighter starts the fan, the blower is initially turned 90 degrees away from the inlet door.
This detail completely confused me when I was reviewing the guide.
It throws a lot of people off.
Right. In a practical exam where the candidate has a relentlessly ticking stopwatch, just 4 minutes and 40 seconds to save a building, wasting precious time starting a massive fan while it's facing sideways, feels wrong.
It does feel wrong.
Why not aim it directly at the door, pull this starter cord, and get that air moving immediately?
It feels highly counterintuitive when you're racing a clock. However, these mechanical fans generate extreme force and vibration.
Oh, right. They're basically huge gas engines.
Exactly. Starting the unit 90 degrees away provides critical safety and equipment control. It allows the firefighter to ensure the combustion engine is running smoothly, physically stabilize the vibrating machine on the ground, and adjust the throttle to the optimal RPM.
So it prevents accidentally blowing a sudden, uncontrolled gust of turbulent air into the fire while the operator is still fumbling with the choke valve or like trying to keep the fan from rolling away.
Exactly. Giving the operator total mastery over the equipment before they commit that high-velocity pressurized air path into a burning structure is paramount.
That makes perfect sense.
Once the engine is fully stabilized, then they physically rotate the running fan to face the opening.
And that rotation introduces a concept from the guide I found just brilliant, the cone of air.
Yes, the cone of air.
The exam rules strictly state that the fan must completely cover 100% of the inlet opening.
And that 100% coverage is absolutely non-negotiable.
Not 99%.
Nope. The cone of pressurized air produced by the spinning blades has to extend beyond all the edges of the doorway, creating a perfect, unbroken pneumatic seal.
I want you to picture standing on your own front porch. Imagine taking an industrial fan and trying to perfectly seal the entire rectangular frame of your front door with nothing but an invisible cone of moving air.
It's a great mental image.
Right. Every single corner, from the top, hinges all the way down to the floor mat. If that seal is only 99% complete, what is the physical consequence?
Well, without a 100% air seal at the inlet, the pressure inside the building cannot build to the required level.
Because it's leaking.
Exactly. The forced air will eddy and swirl, catching the hard edges of the doorframe and escaping back out through those tiny, unsealed gaps.
It just bounces off the doorframe.
Right. The pressure equalization fails entirely. The firefighter has to physically make micro-adjustments, moving the heavy fan a few inches closer, pulling it farther away, or tilting the angle up and down until that seal is utterly flawless.
So the cone of air essentially acts as an invisible, pressurized door.
That's exactly what it is.
It locks the smoke inside the structure. And because of the massive high pressure we discussed earlier, the smoke has absolutely nowhere else to go but straight down the hallway and violently out that smaller, pre-staged exhaust window in the back of the house.
You've got it perfectly. So the fan is perfectly placed, the invisible door is sealed, the trap is set.
But the operation doesn't end on the front lawn.
No, it doesn't. Once the fan is humming and the seal is perfect, the focus shifts entirely to the inside of the building.
Right.
Maintaining this pressure requires strict interior management. The guide details how interior traffic control is a vital component of the procedure.
The operation requires continuous coordination regarding the opening and closing of interior doors, right?
Yes, absolutely.
You are essentially building an invisible highway corridor for the smoke to travel down.
I love the highway analogy.
Every time an interior crew member closes a bedroom door or a bathroom door, they put up a concrete barrier to keep the smoke driving straight down that highway toward the exhaust window.
Exactly. Because opening the wrong interior door, or even leaving, say, a large walk-in closet open, immediately increases the total volume of the space being pressurized.
And what happens then?
That sudden increase in volume drops the overall pressure and creates a new, unwanted airflow path.
So the smoke takes a detour.
Right. The source even mentions a technique where firefighters use salvage covers, which are heavy-duty, impermeable tarps around the fan and the inlet, to physically direct the airflow if the architecture is irregular or actively working against the cone of air.
Sometimes, one fan simply isn't enough to pressurize a large, multi-story or complex structure.
Right. You need more power.
The source goes into escalating the power using a multi-fan matrix.
Yes, this is where it gets really interesting.
So if you have two fans of the exact same size, you place them side by side. That doubles the air volume and pressure, which makes perfect logical sense. But if you have two fans of different sizes, the guide specifies placing them in a line, one directly behind the other.
An inline placement configuration.
Right. And my intuition was entirely backwards on this specific configuration.
Really? How so?
Well, I would have confidently guessed that you put the small fan in front, closest to the door, so that the big fan position behind it doesn't get its massive airstream blocked.
A lot of people think that.
But the guide explicitly mandates the order. The building, then the larger fan closest to the door, then the smaller fan position behind it. Why put the large fan closest to the door?
The mechanics of forced airstreams in an inline setup rely on creating very specific zones of pressure. If you put the small fan in front, the larger fan's massive air column would completely overwhelm it.
Oh, I see.
It would bury the small fan's output, creating highly turbulent, inefficient air that violently spills out the sides and fails to ever enter the building.
So the two airstreams would just crash into each other on the front porch instead of cooperating.
Exactly. By placing the larger fan closest to the building, it acts as a massive vacuum and accelerator.
A vacuum?
Yes. The larger fan creates a low-pressure zone directly behind its own blades. This low-pressure zone efficiently captures and pulls in the forced airflow produced by the smaller fan behind it.
Oh, wow.
It compounds the pressure, cleanly merging the two streams to force a single, unified, massive column of air into the structure.
It is essentially drafting, much like race cars on a track, but utilizing industrial air columns.
That is a perfect way to describe it. Drafting.
But with all this massive compounded air movement, we have to address the nightmare scenario.
We do.
The grave safety considerations listed at the very end of the exam guide.
Because manipulating oxygen and atmospheric pressure inside a burning building means you are playing with the two fundamental elements that fire needs to survive and grow.
You are actively feeding the fire more oxygen.
Yes. Firefighters must continually monitor fire behavior, check structural stability, and constantly watch for fire extension.
Because it can turn bad quickly.
Right. Positive pressure ventilation is a highly effective tool, but it introduces immense risk to the operation. If the airflow changes unexpectedly,
Like what? What could change it?
perhaps a window shatters from intense heat in another room, or a portion of the roof burns through and collapses.
Oh, man.
If that happens, that pressurized smoke highway instantly redirects.
Meaning, instead of pushing the smoke out the back window safely, a sudden change in pressure could pull a wall of superheated fire directly onto the interior crews who are crawling through the halls searching for victims.
Exactly. The final non-negotiable requirement of the exam is that the candidate must be prepared to instantly stop operations if conditions become unsafe. Controlling that invisible air current is a delicate life or death balance.
We started this deep dive talking about a state practical exam that takes just 4 minutes and 40 seconds to complete.
Yeah, a really intense 4 minutes.
Looking closely at the source material, what seems to the untrained eye like simply blowing smoke away is actually a highly orchestrated, terrifyingly precise manipulation of fluid dynamics.
It's an incredible synchronization of skills executed under extreme physical and mental duress.
For sure.
Sizing the exhaust perfectly, sealing the inlet with an exact invisible air cone, calculating inline fan arrays based on blower dimensions.
And managing interior doors like navigating a complex labyrinth, all while a stopwatch is relentlessly ticking.
Exactly. It's a lot to handle.
So the next time you feel a draft in your living room, or you try to clear out the smell of burnt toast by opening a kitchen window and turning on a ceiling fan, think about this.
Yeah.
Think about the massive life-saving control that firefighters exert over those exact same invisible air currents.
Turning the architecture of the building itself into a tool for survival?
Right. But looking at all of this leaves me with one final lingering thought.
Oh, what's that?
Well, we have talked so much about interior doors today, how firefighters rely heavily on closing specific doors to create these pressurized smoke highways and guardrails to force the toxic air outside.
Controlling the interior geometry is really the only way to maintain the pressure corridor to the exhaust window?
Which raises a huge question about how we live today. Think about modern home architecture.
Okay.
Think about how many of us currently live in open concept homes. We spend thousands of dollars remodeling, tearing down internal walls, and removing doors to make our kitchens, living rooms, and dining rooms flow perfectly together.
Right, it's hugely popular.
But by removing those physical barriers, how much does the architectural layout of the places we live silently dictate our own safety?
That is a fascinating point.
With wide open floor plans and zero doors to close on the ground floor, are we accidentally making it incredibly difficult or even impossible for firefighters to utilize these vital pressure tactics if a fire ever breaks out?
Without those concrete barriers, the highway falls apart.
It's exactly. Just something to think about the next time you consider knocking down a wall to open up a space.